Hey, what's up, guys? This is Sheng here. So today, let's take a look at another LeetCode problem here, number 786, case smallest prime fraction. So okay, you're given like a sorted array, integer array containing 1 and prime numbers, only the 1 and the prime numbers. Again, right? So 1 is not a prime numbers, right? So prime numbers starting from 2, and where all the integers of the array are unique. And you're also given like an integer k. So for the fraction, right? So for the fraction, it basically it's a result of one number divided by another number. Okay, and so in this problem, so we have a rule here. So the we have the fraction defined as this one. So array I divided by array j, where I is smaller than j. So this one also means that since the array is sorted, it means that array I is always smaller than array j, right? And also it's because all the numbers are distinct, right? And our task is to find the k's smallest fraction considered, and we need to return the answers of those two numbers. Basically, what are the two numbers, array I and array j, whose fraction is the k's smallest one? Yeah, so that's basically the description of the problem. So we have example one here, right? So for this one, we have four numbers. We have 1, 2, 3, 1, 2, 3, 5. So 3, 5, 2, 3, 5 are the prime numbers. Yeah. And so the output is 2 and 5 because for all the fractions, we have 1, 1, 5, 1, 3, and we sort it. We have 1, 2, 3, 3, right? So this one, 2 divided by 5, is the third smallest fraction among all the fractions. And in example 2 here, of course, since there's only only two numbers in the array here, so that's why it's 1, 7. And here are the constraints, right? So the constraints are 1,000. Actually, it's not that big, and it's also guaranteed that k is valid basically. So k will not be greater than this one because this is the total number of the fractions, right? And then all the numbers of array are unique and sorted in a strictly increasing order. Okay. I mean, the brute force way, of course, is try to get all the fractions among this array here, right? That would be an n square time complexity, right? And then for all those kind of n square like fractions, we do a sort, right? That's gonna be a n square times log n square, right? And that's going to be the total time complexity for the brute force way. And then after this one, we just get the kth element from the sorted list. But that's not obviously it's not a very efficient solution because obviously we're not utilizing this sorted array property here, right? So how can we utilize this one? So if you guys remember the case, for the case smallest fraction, we have a solution, right? We have like we had like a similar problem. Let's say we have like unsorted list. Let's say we have an unsorted list, and then we're trying to get the case smallest one among all those kind of unsorted list. So how did we solve that problem? Basically, we use like the priority queue, right, to help us solve that problem. Since the all the since each list is sorted, we just need to at the beginning we push the smallest element from each of the lists into the priority queue, right? And then we just keep popping from the priority queue. And as long as we have popped, so the case number that we popped out from the priority queue, that will be our, it'll be our like the case smallest, because in the priority queue we're always storing the current up to the length of the least smallest number in the priority queue, right? So that we can improve our time complexity by not enumerating all those kind of all the possible fractions pairs. So for this problem, what are so can we convert that? Can we convert this problem into that unsorted list? The answer is yes, right? If we let's see if we have 1, 2, 3, 5, 11, right, and then 13. What's the next one? 17, I guess, right? So if this is the list of the array here, and assuming, let's say we fix the first number, if we have the first number equals to 1, the more we go to the right side, the smaller the number is, right? So which means that for each of the element, let's say starting from 1 here, the smallest one among all those kind of elements is the first one divided by the last element, which is 17. This is basically 1 divided by 17 is the smallest number by fixing the first element, right? Because this one is greater than the 1 divided by 13, right? Also greater than the also greater than 1 divided by 11, right? So same thing for 2, right? So for 2 is same. So this one is the smallest by given like 2 at the beginning, at the first number, right? This is 2 divided by 13, right? So on and so forth. Similar for 3, right? So now, as you guys can see, now we have like a sorted array already, right? Where the because at each of the index, right? We're using that index, the number on that index as the first element, and then we just simply moving to the left side. We start from the end. Because that will be the smallest one, right? And every time once we pop one element, we pop the current smallest number from the priority queue. We'll just use that index. We use the current index, and then we'll find the one on the left side, and then we push that fraction into the priority queue. So similarly, like how we solve the find the k smallest number among an unsorted list. And then we just simply need to maintain that length of n priority queue, and then we just need to do a k times pop. Okay, cool. So let's try to code that things, right? The first approach where we have n equals to array here, and then we have like priority queue, right? And then to start with, right? So we start from 0 to n minus 2, right? Because we need at least 2 numbers. So we do a priority queue dot heap push, right? Priority queue, and since we need to sort by the fraction, that's why I'm going to store that fraction as the first element into the priority queue, right? And then at the beginning it's O minus 1, right? And while doing that, since we also gonna be after we pop the current one out, we also want to find the next one in the current sorted list, which means we also need to maintain those 2 indices of the current fraction. So at the beginning we have I, the first index is I, and the second one is n minus 1, right? Because we start from the current I divided by the last element, which is the smallest. And then we simply just need to do a while k minus 1. And let's do k here, Mm, we can do k minus 1 here. So basically after doing the k minus 1, so the top one, the first one in the product queue will be the k smallest, right? And so we have this one I and j, right? So heap q dot heap pop product queue, okay? And so we will we'll get the next one when the I is smaller than j minus 1, right? Because if j is smaller than if I equals to j minus 1, then basically those two numbers are next to each other, which means there's no more fractions in this sorted list. So heap q dot heap push, right? And I can just simply copy this part here by with a little bit of modification here. So we have j minus 1, right? So because we're moving to the left, and this is also j minus 1. And then we decrease the k by 1. And then lastly, we simply return the those two numbers on the product queue, on the first one of the product queue, because that will be the k smallest one, right? So the first one is the 1, second one is the product queue dot 0 dot 2, right? Yep. So that's it, right? So if I run the code here, yeah, okay, submit. Okay, cool. So it works, right? I mean, so how about the time complexity for this one? So for the for loop here, we have what? We have n log n, right? Because we loop n times, and we're gonna do a push into the product queue, which is a log n. That's why we have n log n. How about this? How about second one? So the second one is the k, right? So at the beginning we have k times what? Log n, right? Yeah. So that's why the total time complexity will be n plus k times log n. So that's going to be the total time complexity for the priority queue solution. Okay, and there's another solution for this problem, and which is even faster than this one. This is because since we're getting the k smallest, and the array is sorted, I think it's a good candidate by using the binary search. So for the binary search, usually when we do the binary search, we search the answer directly, right? But for this problem, we cannot search the answers directly, because and we want to find the k's smallest fraction considered, and we also want to return the those two numbers from that fraction. It's a little bit of different comparing to the regular binary search. So what we can search for this problem is that we can search the that fraction. So we can search that fraction, and the range for search is from 1 to 0, from 0 to 1. Since it's like I is array I is smaller than array j, so the total all the fractions they are in the range of 0 to 1, and we can simply search this fraction in this range, and by given like a fraction here, right? We want to count how many pairs, right? How many fractions are smaller than the current f, right? So if we can do that, right? If we find all the if we find the count for all the pairs whose fraction is smaller than the current f, and then when we find the count who is equal to the k, then that's the fraction. Basically, that's the fraction we're looking for, right? So let's say, for example, from 1 to 0, at the beginning we have 0 0.5, right? And with 0.5, let's say we have, so let's say k is equal to 7, right? So after our calculation, let's say if there are the count is equal to 5, which means that there are like 5 pairs whose fraction is smaller than 7. Who is smaller than 0.5. It means that, okay, so this fraction is too small. We need a bigger fraction so that we can find the smallest the kth smallest fraction. So which means that we need to search from 0.5 to 1, right? And so the moment when the count equals to 7, then we know, okay, so this fraction, basically this fraction, let's say the fraction is like 0.85. So when the search fraction is 0.585, and then we have a count equal to 7, then we know, okay, so there are like 7 pairs whose fraction is smaller than 0.85, right? But still, even though we have this one, but this is not the answer we're looking for. We're looking for what? We're looking for the pairs. So what are the pairs? So basically, we want to find the pairs that's on the left side. Okay, so we want to find the pairs that's closest to this, who has the fraction who is closest to this 0.85, right? So which means that, assuming we have 0.8, we have like several fractions. We have 7 fractions here. We have this fraction 1, 2, 3, 4, 5, 6, 7. So these 7 fractions are the fractions that's smaller than 0.585. And which is our answer? Our answer is this one. Since we want to find the kth smallest, which is the closest one, right? Which is the one closest to the 0.85. Okay. And yep, so I think that's the idea here. So we do a binary search, and the binary search will basically try to find the proper threshold of this fraction, where we can find exactly smallest smaller fractions. And then the last thing is that we have to find somehow to find this this number, the closest number, right? Comparing to this threshold here. So to do that, what we can do here is that, while we're doing the binary search, we can just maintain this uh, the pairs who is the closest one comparing to the current threshold, right? And then so that, once we have find that thing, we can simply return that value. Okay, I'll try to explain a little bit more how can we maintain these pairs while I'm writing the code here. And so let me comment out these things here. So again, we need, do we need n here? Yeah, I think we need n. So n is going to be array here. And then we have left equals 0, and then right equals to 1. Okay. So while left is smaller than right, right? So we have a middle equals to left plus right divided by 2. So keep in mind we're doing like this decimal. We're not doing this flooring. We are doing this decimal division here. And so for the count, right? So let me try to finish the main loop binary search solution, and then I will add the logic to maintain that pair, right? Who's closest to that to this middle point here, right? So we have a count equals to 0, and in range n minus 1. Oh, and another thing is that for each of the given threshold, the given fraction, how can we efficiently count how many pairs are smaller than that, right? I mean, we don't want to do a brute force all the possible scenarios, because that will beat the purpose of the binary search. So how can we efficiently count how many pairs who are smaller than the current one? So again, let's say we have this 1, 2, 3, 5, 7, 11, and 13, right? So for example, if we have this kind of array here, given like a middle point, we start starting from the first element and the second element. Okay, so this is I and this is J, right? So one of the property, since it's sorted, if the array I, if the array I divided by array J is greater than M, that means that we need to find a smaller fraction, which means that we will move this J to the right, and we keep moving J to the right until this array I divided by array J is smaller than M. So let's say, for example, if after moving J to here, okay, if J has moved to here, and then which means 1 divided by 7, this one is smaller than M. It means that for 1 we have 3 numbers. We have 3 pairs whose fraction is smaller than M, because 5 is 1 divided by 5 is still greater than M, but 1 divided by 7 is smaller. So which means that any numbers after 7 to the end they will all be smaller than the current M, right? So we have J here, and then then we're moving. So which means we have 3 here, and then we're moving I to the right as well. So now I is equal I pointing to here, right? So I pointing to I pointing to 2 here. So for 2, we need to count the pairs, right? Whose array I equals to 2, how many pairs of that is smaller than M. But to calculate that, since it's sorted, we don't have to count J's. We don't need to move J back to here, back to 3. We can simply start from where it has been before. And why is that? No, this is because because we know 1 divided by 7 is smaller than M, and which means that 2 divided by 7 is greater than 1 divided by 7, right? So it means that we can simply check if the current if 2 divided by 7 is still smaller than M, right? If it's still smaller than M, then we know, okay, we have another 3 pairs whose fraction is smaller than M. Otherwise, we keep moving the j's forward to the right side. Right? Maybe another way to explain this problem is that we know 1 divided by 5 is greater than m, right? Because when we try to find the pairs for number 1 here, 1 divided by 5 is greater than m, so which means that 2 divided by 5 is going to be greater than 1 divided by 5. It's going to be greater than m, right? So which means there's no point of checking the 3 and 5 again. So which means that we can simply start checking the j's from where it was before, right? So now, as you guys can see, so since I and j they were always moving to one direction, so that this for loop will be a O of n time complexity, right? Okay, cool. And let's finish what we have left. And like I said, while the j is smaller than n and the array I is divided by array j is greater than m, right? And then we keep moving j's forward. Okay. And what else? So so if the j is greater than is equal to n, we simply break, right? Because if we cannot find so if by moving if j is equal uh after after moving j to the end of the array, if we still cannot find the a valid one, right? So which means the j is now pointing outside of the array here, then we cannot find uh the valid pairs, right? Then we simply just need to break, because even though we move the i's forward to the right side, the fraction will become bigger and bigger, right? That's why we can simply break when the j has moved outside of the array here. Otherwise, we just increase the count. Since j's on the left side are all the pairs which are greater than the current threshold. Anything that's on the right side is smaller. That's why we do n minus j, right? And yeah, so and after this one we do a simple check. So if the count equals to k, we think we'll return here. Else, right? Else, if the count is smaller than k, basically we'll discard the left part, right? Otherwise, we discard the the right part. So this is the basic for loop. Sorry, the basic binary search template. But now the problem is that how can we find this p and these two numbers? Like I said, we want to find the closest number, the closest the fraction, the number the fraction that closest to the middle point. Okay. And how can we find that? We can simply just define like maybe another p and q, right? And every time when we find like the current smallest, the current is basically the biggest number, right? For the current loop here, we can do a check here. So if this array I divided by array j is greater, we can have like a max fraction here, right? Equals to starting from 0. If that's the case, we do a p equals to a I array I, right? And then q equals to a array j. And then we just update this max fraction equals to the p divided by q, right? And here I just simply return the p and q. So what we're doing here is that let's say we have again, right? We have 1, 2, 3, 5, 7, and 11, and 13, right? So let's say we stop at, let's say I is here, right? And j is here. So when we stop here, so I and j are the first pair who is smaller than the m, right? Uh, given this I is the p, is the first number, right? Which means it is also the biggest one. With this I, I as the denominator, right? Because if we move the j's moving forward to the right side, so the fraction will become smaller and smaller. Okay, right? So which means since we're trying to find basically the number who has the biggest fraction, right, among all those kind of candidates here, that's why the current j will be the biggest one, given fixing this I here. That's why we can simply use this one to, we can, every time we find the first pair, right, who is smaller than the f here, we can just use that smaller than the m here. We can use that pair to update this p and q, because and after this one, so we will find, basically we'll find the biggest fraction, a biggest fraction among all those kind of candidates, among all those fractions who are smaller than m, which is exactly what we're looking for of x here. Okay. Yeah, I think that's it, right? So if I run the code, oh, I haven't defined the j yet. So j starts from 1. Okay, cool. So as you guys can see, this one is much faster, right? And why is that? This is because we have like a while the loop here from left to right, and inside here is also it's an n, right? So we have n times what? 10 times n times log something. This log is what? It's a range. It's a range between L and R. And what's the range? So this is the range actually. And I think it's basically the precision is how many decimals is between 0 and 1 we're looking for here. I think it's kind of normal to assume this one is like 10 to the power of 9, because I think with precision of 9 digits of 9 decimals, so this one should be accurate enough, because when we have 0 to 1, it will be divided to 0.5, and then 0.5 will be divided to 0.25, right? And then 125, and then so on and so forth, right? So it'll be divided to a lot of decimals. I think 9 decimals should be enough, should be accurate enough. That's why we have n times log this, which is pretty fast, close to n, right? Okay, cool. I think that's pretty much everything I want to talk about for this problem. And yeah, thank you for watching this video, guys. Yeah, stay tuned. See you guys soon. Bye bye.